You know, every powerful AI model has a hidden vulnerability, and it has nothing to do with the code or the original data. It's about time. Today, we're going to dive into the critical art of knowing exactly when to retrain your models to keep them smart and sharp in a world that, well, never stops changing. Okay, so you've done all the hard work. You've built this amazing AI model. It's out there in the world making predictions, driving decisions, but it's hiding something from you. And that secret is, it's getting dumber every single day. Seriously, the incredible accuracy it had on day one, it's fading. So the big question is, why is this happening? And more importantly, what can we actually do about it? So here's our game plan for this explainer. First, we're going to get to the bottom of why models degrade in the first place. Then we'll unpack 3 smart triggers for retraining, using a simple schedule, watching for performance drops, and detecting changes in the data itself. And finally, we'll see how it all comes together in a fully automated system. All right, let's tackle this head on, the core problem. Think about it like this. A deployed model is basically a snapshot in time. It learned everything it knows from data from the past, but it's forced to live and operate in the present, where everything is different. And this table here, it breaks down the reasons perfectly. First up, you've got data drift. This is when your input data changes. Maybe your user base suddenly skews much younger. Then there's concept drift. This is sneakier. It's when the meaning of what you're predicting actually changes. Think about fraud detection. Criminals are always coming up with new schemes. And of course, there's good old seasonality. Holiday shopping behavior looks nothing like it does in the middle of summer, right? And listen, this isn't just some abstract technical problem. The consequences are real, and they hit you right where it hurts, the bottom line. When a model gets stale, its accuracy plummets. That leads to bad decisions, which can mean real financial losses. And maybe worst of all, it just completely erodes people's trust in your entire AI system. So how do we fight back against this decay? I mean, we can't stop the world from changing, but we can build our models to adapt to it. And the key is using intelligent signals, we call them triggers, to tell us exactly when it's time for a refresh. And that brings us to our mental toolbox of 3 core strategies. We can retrain based on a simple calendar, we can wait until the model's performance actually starts to dip, or we can be really proactive and watch for the data itself to change. Let's break down each one. Okay, our first strategy is definitely the most straightforward of the bunch. We're just going to retrain based on the calendar. The idea here is really simple. You just pick a time interval, could be daily, weekly, maybe monthly, and you retrain that model like clockwork. You can think of it like a scheduled tune-up for your car. It's happening whether it seems to need it or not. And the real beauty of this is its simplicity. It's super easy to set up. It's predictable, it's reliable. But there are definitely trade-offs. You might be burning compute cycles and money retraining a model that's actually doing just fine. Or even worse, what if a huge market shift happens the day after your scheduled retrain? Well, your model's going to be flying blind until the next cycle comes around. And the right schedule, of course, depends entirely on the job. For something super volatile, like stock market predictions, a daily retrain makes a lot of sense. For something like a recommendation engine, maybe weekly is fine. And for long-term sales forecasting, monthly or even quarterly could be the perfect rhythm. But just retraining on a schedule can feel a little wasteful, can it? So what if we only retrained when we absolutely had to? Well, that brings us right to our second strategy, and this one is all about performance. So with this approach, you basically draw a line in the sand. You pick a really important metric, like accuracy, and you set a rule. You might say, if this model's accuracy ever drops below 90%, that's the trigger. It's a totally reactive strategy that only springs into action when there's proof of a problem. The huge advantage here is efficiency. You only spend resources on retraining when it's actually needed. But the major catch, and it's a big one, is that you need a constant feedback loop with fresh, labeled data to even know how your model is performing. And getting that ground truth can be really tough, especially in real-time systems. This visual makes it crystal clear. Imagine your model launches at a fantastic 95% accuracy. Awesome. Over time, it slips a bit to 93%, then 91%. Still pretty good. But the second it crosses that threshold you set and hits 86%, bam, the alarm bells go off and the retraining process gets kicked off automatically. Okay, so the first 2 methods we talked about are both reactive in their own way. They wait for something to go wrong.
But what if? What if we could get ahead of the problem? What if we had an early warning system that catches issues before performance ever takes a hit? This is where the super powerful concept of data drift comes into play. Instead of watching the model's output, its accuracy, we're going to watch its input. We monitor the live data coming in and we look for any significant statistical changes compared to the data the model was trained on. It's literally an early warning system that spots trouble on the horizon.
Now we can actually put a number on this using metrics like the Population Stability Index, or PSI. Don't worry about the fancy name. Just think of it as a score that measures how different the new data is from the old data. And as the slide shows, we can set really clear rules. A low PSI score, say under 0.1, means everything's stable. If it's in the middle, we keep an eye on it, but if that score jumps above 0.25, that signals a major shift, and we trigger retraining right away.
So we have our three triggers. We've got the schedule, the performance drop, and the data drift. But a trigger is just the first domino to fall. How does it fit into a bigger automated system? This is where we zoom out and start talking about MLOps, which is all about building these robust, repeatable pipelines.
And this flowchart lays out the whole assembly line perfectly. It all starts with collecting new data from your production environment. Then, step 2 is where our triggers live. That monitoring system is constantly checking for performance drops or data drift. As soon as a trigger fires, it automatically kicks off the entire retraining pipeline. The new model gets built, it gets tested on the side in what's called a shadow deployment to make sure it's actually better, and only then does it finally replace the old stale model.
So let's bring it all home. This summary table right here is your cheat sheet. Use a schedule-based trigger when you're in a pretty stable environment and routine refreshes are all you need. Go for a performance-based trigger for those business-critical applications where accuracy is absolutely everything. And you'll want to use a drift-based trigger when you're in a really dynamic world where the data patterns are always shifting under your feet.
You know, I think this quote just says it all. A model that's just sitting in production isn't a finished product. Retraining isn't some chore you do every once in a while. It's the very heartbeat that keeps your AI alive, adapting, and most importantly, valuable.
Look, the world is not going to stop changing. That's a given. So your models can't stop either. The real question I want to leave you with is this. Now that you know the triggers, how are you going to build systems that don't just predict the future, but actually evolve with it?